तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last time I had introduced a new quantity, namely the electrostatic potential, by showing that a particular integral of the electric field depended only on endpoints. Let us review. If you have a charge and it is sitting at the origin, charge q, and if I took another charge small q and took it on some path from a position r naught, so r naught is this vector, to another position r, and you went however you liked, then the electric, then you can write an equation which says go from r naught to r along this path C. So, usually you do not write the endpoints if you write C, and you work out what this integral is. What this integral means is I choose a lot of points along this curve and I draw little arrows, and on each arrow I find the local electric field and I compute E dot dl1, then I add E dot dl2, etc., and I take that whole sum, and then I let dl1, dl2, dl3, etc., become very small. In other words, I put more and more points on this curve uniformly, so that these arrows become very small. When I do that, I am essentially having an integral, and that is the integral that is meant here, integral r naught to r of E dot dl. Now, in general this integral would depend on how I went from r naught to r. However, we saw last time that if you work this integral out for a charge placed at the origin, you find that this integral becomes the charge q over 4 pi epsilon naught times integral r naught to r of r divided by mod r cubed dot dl. But this direction r at any point is pointing outwards. This dl points in some general direction, but dl dot r only cares about that part of dl that is along the radial direction. So, you can take this entire integral and replace it with an integral that is only in the radial direction. So, you find the radial part of r naught, call it rho naught, radial part of r, call it rho, and then you are really only now concerned with the radial direction d rho, and r over r cubed d rho. So, this becomes a scalar integral, and when you work it out, you find that this is nothing but integral rho naught to rho d rho over rho squared, which is equal to minus 1 over rho between the limits, which is 1 over rho naught minus 1 over rho. So, here rho is nothing but the radial coordinate of r, and what you are seeing is the electric field dotted with dl integrated from a point r naught to a point r along some path, could be any path, is equal to q divided by 4 pi epsilon naught times 1 over rho naught minus 1 over rho, where rho naught and rho are the r coordinates of the beginning and the ending point. It does not depend on how you got there, it only depends on where you started from and where you ended up. I could have gone this way, or I could have gone this way, or I could have gone this way, it does not matter. All that matters is the beginning and the final value of the radial coordinate. When this is the situation, then we can call this a function of the final point alone, and is called the electrostatic potential, which is a function of position. In fact, in this case it is a function only of the radial component of that position. Okay. So, this is what we call the electrostatic potential, but we have derived it only for a charge kept at the origin. Supposing the charge was not at origin, supposing it was somewhere else, supposing my charge is sitting here. So, the distance from the origin to the charge is a distance I will call r prime. It is very standard in electromagnetics that when I use a symbol r, I mean observer, and when I use a symbol r prime, I mean source. So, this q is generating the electric field, it is the source of the electric field, so I use r prime. Now, I have got some curve going from r naught to r. This equation will not work, because this equation assumes the charge was at origin. However, what is this origin? The universe does not really have knowledge of an origin. Universe does not say this lab is the center of the universe, it does not say the center of the Milky Way is the center of the universe. If we put origin here, it is in our minds, universe does not define it. So, we might as well put an origin at the charge. Now, if you put the origin at the charge, we know the answer. We know that the electric field r naught to r of E dot dl is equal to some phi, which is a function of r and not of how we got from r naught to r. So, how can we take this information and use it in general? Well, the answer is quite easy. What we do is we say, let us consider a new variable called u, which is equal to r minus r prime. Now, as we move on this curve, what is changing is r. So, I will do a change of variables, du is dr minus 0, because r prime remained constant. So, du equals dr. So, what is that saying? That is saying that if I take a point on this curve, earlier I had this was r, now I have from the new origin I have u, and they are different vectors. But if I now go to the next point, that is r plus dr, that corresponds to u plus du. And when we changed coordinates like this, r plus dr minus r, that is the dr, is nothing but u plus du minus u. So, it says du and dr are the same thing, even though I changed coordinates. So, my coordinates are now very different, but the change in u and the change in r are the same, and it is only the change that I concern myself about when I do an integral. It is dl that comes, not L itself. So, let us see where this transformation of coordinates takes us. So, we start with the integral r naught to r1. I am changing this final point to r1 because I used r for the intermediate point as well. So, r naught to r1, the electric field dot dl, that is where we start. Now, I will change my coordinates. I will go to this coordinate system, u equals r minus r naught. So, that is like working in this coordinates, because this is u and this is u plus du. So, when I do that, the integral becomes u naught to u1, the electric field as a function of u dot du. And I already know that du and dl are the same thing. So, that is why I am able to write this. U naught is nothing but r naught in the u coordinate system, that is, it is this vector starting from this origin to r naught, and u1 is this vector starting from the new origin to r1. But in this new coordinate system, my charge q is sitting at the origin, which means I know how to write down the electric field. I can write it down. It is integral u naught to u1 q over 4 pi epsilon naught u over u cubed dot du. So, this is the electric field in the u coordinate system dot du along the curve. But this is the problem we have already done. We have already done the problem of integral of E dot dl when the charge is at the origin, and the answer we got for that was it is equal to q over 4 pi epsilon naught integral. I replace the vector by just the distance, the radial distance from the origin. So, without the line underneath, this is just a radial coordinate u naught to u1 du over u squared, and the integral became, as we saw last time, q over 4 pi epsilon naught 1 over u naught minus 1 over u1. But what is u naught? U naught is the magnitude of the vector u naught, is the radial length. So, that is the magnitude, but u naught itself is defined by this equation. So, it is equal to magnitude r minus r naught. Similarly, u1 is equal to magnitude r minus r1. Sorry, I think I made a mistake there. It is equal to r naught minus this is r minus r prime, r naught minus r prime, and this is r1 minus r prime. So, I substitute these in here, and what I get is q over 4 pi epsilon naught 1 over magnitude r naught minus r prime minus 1 over magnitude r1 minus r prime. So, once again, even though the charge is not at the origin, this integral turned out to be a function only of the initial position, the final position, and of course, where the charge is. It did not depend on how we went from r naught to r1. That got taken care of by evaluation of this integral, and the integral depended only on how, where we started and where we ended. It did not depend on the root. Now, usually we take this initial point such that it does not contribute at all. For instance, in 3D we will choose this to be infinity, in which case we get integral r naught, which is infinity, to r1. Now, I am going to just call it r. E dot dl is equal to minus q over 4 pi epsilon naught 1 over r minus r prime. What this means is that we can again define a function, a scalar function, which is derived from the electric field. So, we will define potential phi of r, which is equal to minus integral infinity to r of E dot dr. However, we come from infinity to r, this answer will be unchanged. It only depends on the fact that we came to this point. So, this is a generalization. It means that regardless of where the charge is, whether it was at the origin or not at the origin, my potential function is the same. And now, I have one more generalization. I can put many charges q1, q2, q3, qn, and I can use this same technique, and I can say integral from infinity, this is the symbol for infinity, an h that is turned horizontal, to r E dot dl. This electric field is due to all these charges. So, I can write this as infinity to r summation over say k equals 1 to infinity 1 to n q sub k over 4 pi epsilon naught well, let me call this r1 after all, okay. R minus r prime k divided by r minus r prime k cubed dot dl. Now, each of these terms is nothing but this integral that we have already done. So, the answer must therefore be just the sum of all these answers. So, it becomes equal to sum k equals 1 to n q sub k over 4 pi epsilon naught 1 over r minus r k prime, and this will now be r1, the limit r1. So, I have now an expression for potential. This is actually the negative of this is what I want. So, minus 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 that became minus, so this is plus, phi of R1 is equal to. So, this electrostatic potential is the sum of electrostatic potentials due to each charge Q1, Q2, Q3 up to Qn. Now, this potential is completely fictitious. At least as far as the electric field is concerned, we know there is a force. Therefore, we can say we believe there is a force per unit coulomb. But as far as the electric potential is concerned, there is no way of measuring the electric potential. However, it is an extremely useful idea, because you see the electric field has three quantities in it. So, there is a electric field along x, an electric field along y, and an electric field along z. So, it is a complicated field, it has three components in it, but the electric potential phi has only one component, phi itself. So, it is a much simpler concept than the electric field. So, I have gone down from having three pieces of information at every point to having one piece of information at every point. But there is more to it than that. If this is all I was doing, for example, supposing a plane is flying over ground. Okay, so, the plane has a location, and this R would have x, y and z information. X and y talk about where horizontally it is, z is how much higher than ground. Now, I could ask what is the altitude of the plane. That maps from this 3D value to just z. So, that also is like going to a very simple idea. So, you could think of finding altitude, finding height, which takes a 3-dimensional vector and gives me back an answer. It is 1 kilometer above the ground, and finding potential. I go from electric field, which is Ex, Ey, Ez, to a single value phi. So, it looks like I am doing the same sort of thing, but there is something very surprising. If I told you the height of the plane, you could not tell me where the plane is. You can only tell me the height of the plane. You can't tell me that it is 100 kilometers east of Madras. But if you are trying to, if you give me the electric potential, it so turns out I can tell you what all these three components are. It is the information that is inside phi is enough to reconstruct the entire electric vector. This is an extremely unusual thing. In fact, what it means is that the electric field is a very simple field. It is not really a vector field at all, that in some sense it is so simple, its entire information is captured in a scalar field. Now, let us show this. Supposing we have found potential. So, we know that for a point source, phi is equal to q over 4 pi epsilon 0 1 over magnitude r minus r prime. This is what the potential is. Potential itself is a function of r, and the point source q is at a point r prime. All right. Now, I want to go from knowing this potential to knowing this field, and I am claiming that unlike in the case where I am giving the height and asked to find the plane, and I can't do it, in the case where I am given the electric potential, I can find the entire electric field. Let us see how we do it. First things first, if I have got an electric potential phi of r, this is a scalar field. It means there are numbers associated with every position. This electric potential came from an integral. Now, I am sure you know that when we integrate things, we get smooth functions. In other words, integral of any function is continuous. So, what it means is phi is smooth. Now, what does that mean? It means that phi is like temperature, phi is like the height of a mountain. I can draw contours of phi. So, I can, if I work only in x and y, I can draw contours. This is x, this is y, and I say that phi is 4 volts, 5 volts, 6 volts, and so on and so forth. So, I have, because it is a smooth function, I have the ability to draw surfaces on which potential is constant. Now, what is the advantage of this? Supposing I look at this part alone, I am going to blow it up. The 5 volt surface looks like this. The 6 volt surface looks like this. They are both slightly curved, so I have drawn them slightly curved. Now, I am sitting here and I move in some direction, and after I move some distance, call it dl, I go from phi of 5 volts to phi of 6 volts. However, we have a separate result. We know that phi of r, whether it is 5 volts or 6 volts, is equal to integral r naught to r of electric field dot dl. And it says it does not care how you got there. If you start at r naught and reach r, however you reach it, it is phi of r. So, now let us see how that works. Let us say that my point r naught is here. To calculate phi at this point and find that it is 5 volts, I have done an integral and come here. To find that phi at this point is 6 volts, I did another integral and came there and said the difference in potential is 1 volt. But this curve C1 and this curve C2 are completely arbitrary. I can choose any curve I like for C1 and C2. So, specifically when I choose C2, I do not choose this one. I am going to choose a curve that looks like this. I am going to retrace C1 itself, go along C1, come to 5 volts, and then I will move along dl itself and reach there. So, what does that mean? It means I did integral E dot dl in order to do this integral. I am going to do it as integral from r naught to r to this point E dot dl plus this piece. E of r dot dr. What have I done? I can calculate this potential any way I like. I can go on any curve I like, but I chose to go to that curve which touches r before it goes to r plus dr. This part of the curve is this, and this additional part is this. And you know that if you have an integral a to b of some f of x dx, you can always write a to c f of x dx plus integral c to b f of x dx. So that is what I have done. I have broken it up into two pieces. The second piece is very simple, it is just E dot dl. But this first piece I know the answer already. This first piece is nothing but phi at r. I am sorry, here this should be phi of r plus dl. So I have an expression which says phi at this point r plus dl is an integral r naught to r plus dl of E dot dl, that is by definition. I have broken it into two parts, one part which goes to r and E dot dl, and this part is nothing but phi of r itself. So if we write it out now, we have an equation that says phi of r plus dl is equal to phi of r plus E dot dl. Of course, it assumes that dl is very small, so that second integral is E dot dl. I can take this phi of r to the other side, and I can write it as phi of r plus dl minus phi of r is equal to E dot dl. This is the delta phi. Now, if we divided both sides by dl, then in a certain sense we get E. I mean, you look at this equation, it is sort of saying, I am going to put this within quotes, d phi dl is equal to minus E. Well, there is a minus sign coming somewhere, the whole thing has minus, right. So phi is minus of this, so there is a minus sign, so it is minus E. Okay. Except we do not know how to define this quantity, we do not know how to say derivative of a function with respect to a vector. It is a very funny kind of derivative. We understand things like df dx, df dy, but what does it mean to say df dl? Let us look at this diagram again. I have 6 volts, I have 5 volts, I started at a point r, I went to r plus dl. And I am saying that this delta phi is equal to the electric field at r dot dl. Now, there is another way of calculating delta phi. Supposing these were straight lines, okay, and they are for very small distances, they are straight lines. So, if they are straight lines, you can draw this diagram as phi equals 5 volts, phi equals 6 volts, this is my dl and this is r. I can draw a normal between these two planes and I can take the angle between them, that is theta. If this distance is d, then it is clearly true that d is equal to dl cos theta, because this is the diagonal, this is the base. So, d over the diagonal is cos theta. So, d is equal to dl cos theta. So, in a certain sense, when I look at delta phi, I am saying move along any direction you like till you go a distance along the base which is equal to d, because if I went at a different theta, if I went along an angle theta 2, I would have to go a different distance dl, but I would have to go that distance dl such that my base was equal to d. So, I can write the same relation as delta phi is equal to d phi dl times d phi dn times dl cos theta, meaning go in this direction, this is the n direction, go in this direction, how far? You go in this direction, this length cos theta, you would have gone therefore a distance d. The answer is you would have gone a distance, so you changed phi by delta phi. Now, if you look at these two, this equation, you have one magnitude, you have a second magnitude, and you have cos theta, and we know a vector operation that introduces cos theta. We can call this d phi dn along the normal direction dot dl. All right. I want to repeat the steps I made so that you are with me. First of all, we have a reference somewhere, R naught. When I calculate potential at any point, I am doing integral R naught to R of E dot dl with a minus sign. I have not kept the minus signs properly. So, I integrate from R naught to R, and I integrate from R naught to R plus dl. They give me different answers for phi, and the difference in the answers is what I call delta phi. Now, I can calculate this delta phi in a clever way by saying the phi at this point is equal to calculating this integral E dot dl up to this R and then integrating along dl. That gave me that the change in delta phi is only this piece E dot dl with a minus sign, okay, a minus sign here. So, I have delta phi is equal to minus E dot ER dot dl, and I can calculate the same delta phi in a different way. Namely, I can say that if I move in any direction, I move a distance dl. It is equivalent as far as the change in phi is concerned with moving in the normal direction a distance dl cos theta. That is, the normal distance I move is the sloping distance I move times cos theta. The change in potential is nothing but the change in potential as I move in this shortest direction times this projected distance, which can be written as a vector operation. That is, I am constructing a special vector, a vector whose direction is the direction of the normal, whose magnitude is the derivative along this direction. Now, look at these two equations, both are equal to the same thing. So, I can write minus E dot dl is equal to d phi dn n hat dot dl. which means I can write that the electric field is equal to minus d phi dn along n hat. Now, the textbook gives the algebra, so you do not have to really understand the algebra that much, but what is important here is that from the electric field I did an integral, I got a scalar quantity. I can do that for many fields. As I told you, if you tell me the location of a plane, I can tell you its height. That is like extracting a scalar field out of a vector field. But given the height, I cannot locate the plane. Given the height, I only have the height. I do not have the x and y coordinates. But this is a case where given the scalar field phi, I have now gone back and found the vector field E. So, it says the electric field is particularly simple. It is so simple that given the electric potential, I can calculate back the electric field. This is one of the reasons why the electric potential is so useful, because by working with a single scalar quantity, I have found out a vector quantity. By studying a function of with one component, I have actually solved for 3 components, and therefore there is a great saving in labor. The best way of showing that it is a useful idea is to work out a problem. Couple of lectures ago, I derived what the dipole field, the field due to a dipole is. I did that because I wanted to show that the Coulomb field does not fall fast enough. If you remember, I was looking at the problem that the Coulomb field was 10 to the 36 times, 36 orders of magnitude times stronger than the gravitational field. So, one of the explanations that is given is there are equal numbers of positive and negative charges. So, I said let us assume these charges are separated by a distance of 1 angstrom, and let us work out what the field would be. And at that time I used Coulomb's law and calculated the field. Let us do the same thing with the electrostatic potential. So, I have a charge capital Q, I have another charge minus Q, this is the z direction, and some distance far away is an observer. So, I am putting my origin here, and this is the position r. So, this distance between the charges is a distance d, and I have this is r minus r1, this is r minus r2. As we worked out, the electric field at r is q over 4 pi epsilon naught times r minus r1 divided by magnitude r minus r1 cubed minus r minus r2 divided by magnitude r minus r2 cubed. It is a vector quantity, it depends on r, depends on r1, and it depends on r2. And at that time I did not want to do all the algebra, so I only worked out roughly what the r dependence of this vector field is going to be. Now I can work out what the electric potential of this is. We have already worked it out. Phi of r is equal to q over 4 pi epsilon naught 1 over magnitude r minus r1 minus 1 over, that is, the electric field depended on the direction and the magnitude of each of these lines. The electric potential depends only on the distance, it does not care about the direction. It is an enormous simplification. Why is it a simplification? Supposing I wanted to find out what this field is for r much greater than d. So, I am talking about a point which is far away. Then what is going to happen? These two lines, let me redraw this because it is not drawn very well. These two lines are nearly parallel. By that I mean this angle delta theta is nearly 0. So, these lines are nearly parallel, which means that if I drew an arc with this line as my radius, actually it will look like this, and it is essentially a straight line. How much is this distance? Well, this position r has an angle with respect to the horizontal, theta. That same angle shows up here. And so, this distance becomes d sin theta. If you chose your angle the other way, which is what the book does actually, you will get d cos theta. So, now let us see if we can work out what phi should be. I am going to take common denominator. So, phi of r equals q over 4 pi epsilon naught times mod r minus r2 minus mod r minus r1 divided by the product of the two, r minus r1, r minus r2. So, it is the difference in distances between r and these two charges divided by the product of the distances. Now, each of these distances is more or less equal to net distance r. So, the denominator can be simplified. So, what you get is phi of r is equal to q over 4 pi epsilon naught times the difference in distances we worked out is d sin theta divided by the denominator is nothing but r squared. It is an approximation. Two approximations are involved. One is that if I put a right angle line here, it is equivalent to saying it is a arc. This is a very good approximation. The second approximation is that the product of these two distances is approximately r square. So, both of these are very good approximations for charges that are far away. Now, why do I call this an advantage? I mean, I have calculated phi, but how does it help me? Well, now all I have to do is to go from phi to E. So, I need to do electric field is equal to minus d phi dn n hat. I can plot out this phi, I can find the what are called equipotentials of phi, and if I navigate along the normals to those potentials, I get the electric field out of it. Now, there is a standard mathematical machinery to carry out this action. Let us try and see how we can do it. If you look at what we did earlier, we said delta phi is equal to d phi dn n hat dot dl. So, in a certain sense what this is saying can be written out. This piece I will keep d phi dn n hat dot dx along x plus dy along y plus dz along z. So, this quantity has an x component, it has a y component and a z component. So, it is equal to d phi dn along x dx plus d phi dn along y dy plus d phi dn along z dz. The component along x, the component along y, the component along z. But we also know that this same quantity is equal to minus E dot dl. So, this same equation can also be written as minus Ex dx plus minus Ey dy plus minus Ez dz, which means that Ex is nothing but the x component of this normal derivative, Ey is nothing but the y component of this normal derivative, and Ez is nothing but the z component of this normal derivative. Now, if you know your partial derivatives, you know that if you have any function f of x, y, z, then you know that df is equal to del f del x dx plus del f del y dy plus del f del z dz. This is a standard result in mathematics. And here we have d phi is equal to d phi dn along x dx plus d phi dn along y dy plus d phi dn along z dz. So, if you just look at these two, it becomes obvious how to calculate this d phi dn. So, I have three equations. Let me write them all here. This d phi is equal to this. It is also equal to del phi del x dx plus del phi del y dy plus del phi del z dz. It is also equal to minus Ex dx plus minus Ey dy plus minus Ez dz, and they are all equal to each other for any dx, any dy and any dz, which means these coefficients are saying the same thing, these coefficients are saying the same thing, and these coefficients are saying the same thing. So, I can write down Ex is equal to minus del phi del x, Ey equals minus del phi del y, and Ez equals minus del phi del z. This procedure of extracting three values out of one function is given a name. It is called the gradient, and it is also given a symbol. So, we write the electric field is equal to minus inverted triangle phi, and when we write this, we mean this. We mean that the inverted triangle phi is a vector whose x component is del phi del x, whose y component is del phi del y, whose z component is del phi del z. So, minus of that puts in a minus sign for each of these. Now, this is in Cartesian coordinates. What happens if we do not stay in Cartesian coordinates? Up to now we have worked only with x, y, z, but it turns out that there are many interesting uses of cylindrical and spherical coordinates. So, let us look at a case where we want to go away. Let us say we have spherical polar coordinates. Spherical polar coordinates, as I remember talking about a little while back, you have the radial direction, you have a theta direction, that is the angle with the z axis, and you have a cone that is traced out by this vector if you rotate it around the z axis. That point, if you take this point and project it onto the xy plane, you get a vector in the xy plane. This is x, this is y, there is an angle here. This angle is called phi. So, you have z is equal to r cos phi, cos theta, sorry, that is, it is the this height. Square root of x squared plus y squared is equal to r sin theta, that is this length. The x coordinate itself would become r sin theta times cos phi, because this length is r sin theta, and you have to multiply that r sin theta to get by cos phi to get the distance along x. Similarly, y is equal to r sin theta sin phi. This is an exceptionally useful coordinate system. We should know all about it. But in this particular case, what I am interested in finding out is, if I wrote the potential phi as a function of r, theta and phi, what can I get if I want to get the gradient? Well, the answer is that I want to know what delta phi is. Delta phi is del phi del r, delta r, plus del phi del theta, delta theta, plus del phi del, well, I should use a different symbol, delta phi. So, this is nothing but, if I have a function of 3 variables, the change in the function is given by this expression. But I also want to know what is dl. dl is delta r along the r direction plus r delta theta along the theta direction. So, along the r direction I just go, but along the theta direction, if I increase in theta by an amount delta theta, this distance is r delta theta, and then it is equal to r sin theta delta phi along the phi direction. I put a twiddle over the phi's to separate it out from the electric potential. Where did this r sin theta come from? Well, the projection onto the xy plane is r sin theta, and if I change phi, this distance is given by r sin theta delta phi. Now, if you look, I want to say delta phi is equal to minus E dot dl. So, I have to read off, this is the dl part, this is the delta phi. So, what are the components of E? So, minus Er is del phi del r, minus E theta is equal to 1 over r del phi del theta, and minus E phi is equal to 1 over r sin theta del phi del third angle. I will come back to this the next class, but this will allow us to calculate the electric field out of a dipole. Thank you.